page of notes. We're going to go through this proof here, not because you need to be able to regenerate it. We're not doing this proof because I'm worried that someone's going to need to be convinced that the derivative of the natural log of x is equal to 1 over x. I'm pretty convinced that everybody will accept this as fact. But the reason it's worthwhile going through this proof is because it involves the second definition of derivatives, and it involves looking at limits. So for that reason, it's a worthwhile proof to go through. So we're going to start by reminding ourselves of the second definition of the derivative. So if we're looking for the derivative of the natural log, well, we can define that, or we have defined that as the limit as h approaches 0 of rise over run, right? So we're doing f of x plus h minus f of x all divided by the run h. And then here we're going to use the natural log as our function. So we're looking for the limit as h approaches 0 of the natural log of x plus h minus the natural log of x all divided by h. And then here, as we've written this, the natural log of blah minus the natural log of this other thing should remind you of those rules that we did on the other side. We're going to rewrite this using the log rule. So the limit as h approaches 0, I'm going to pull out the dividing by h out here as the first factor. And then this is going to be the natural log of the first x plus h divided by x. And then we're going to simplify this. And what we're doing is we're kind of putting this in a form that gets us toward this right up here. And this right up here is the definition of E. And if you remember back in pre-calculus or algebra 2 and trig, when we were doing compound interest, this is the compound interest formula that we have here. And if you compound continuously, so as you compound instead of once a month or once every year, once every day or once every hour or once every second, as the amount of time you compound gets closer and closer to infinity, what happens is that amount ends up being E. Right? So this right here is the mathematical definition of E. And we're starting, if you look in here, we're going to try and move this around, manipulate this so that we can get something that looks like this. All right? So we will rewrite this. Oops, we want to be using the correct pen here. Give me a second. My apologies. All right, here we go. We want the limit as h approaches 0. And we're going to do again a log rule, the exponent log rule. So we're going to take this 1 over h and we're going to make it the exponent here. Right, so we're going to have this form 1 plus something over something else raised to a power. Right, so this is going to be the natural log of x plus h all over h. And actually, let me rewrite this while I'm here. So this is going to be x divided by x plus h divided by x. So let me write that instead, which would be 1 plus h over x, and then all of that is going to be raised to the 1 over h power. Right? And now to do a little bit more manipulating here. We're going to define a new variable. We're going to say let's let w equal x divided by h. And if w is equal to x divided by h, the first thing we can notice about this is that as h approaches 0, right, which is what's going on here, as h approaches 0 in our limit, well, w is going to approach infinity. Right? So I'm going to start to rewrite this limit. We'll do this in a slightly different color now. So instead of writing h approaching 0, we've just decided if we're going to let w equal x divided by h, well then h approaching 0 is comparable to w approaching infinity. W approaches infinity. And we're going to do the natural log of 1 plus, now this here, h divided by x, well, if we take this and just simply take the reciprocal of this equation, what we would get is h divided by x equals 1 divided by w. So over here I'm going to replace h divided by x with 1 divided by w. And then the exponent 1 over h is going to be the same thing as x, 1 over h is going to be the same thing as w over x, right? So we would take this equation over here, this would be comparable to w h equals x, which means then that h would be equal to x divided by w, and then 1 over h would be equal to w divided by x. So this 1 over h is going to be comparable to w divided by x. Right? Now, actually we'll do one more. We're going to rewrite this. Right? So this is a fractional exponent. I'm going to pull apart the fractional exponent. So we'll start again. The limit as w approaches infinity. Pull apart the fractional exponent. So this is going to be the natural log of, we will have 1 plus 1 over w raised to the w, and all of that raised to the 1 over x. And now here, what I've done this algebraic manipulation to get this in here, right? So we've got the limit as w approaches infinity of this here, right? And this, as w approaches infinity, this in here is e, right? So let me just make a little note for ourselves, right? That all of this, as w approaches infinity, all of this is really e. So now we can rewrite this as the limit as w approaches infinity of, and I'm going to take this exponent here, use my log rule, natural log rule, so I'm going to bring that down as the coefficient in front. So this would be the limit of, as w approaches infinity, of 1 over x times the natural log of e. Well, the natural log of e is 1, and the limit as w approaches infinity of 1 over x, well, it's 1 over x. There is no w involved whatsoever. So this is just simply equal to 1 over x. And what we've done is we've proved that The derivative of the natural log of x is 1 over x. Done. Or in mathematical speak, quod erat demonstratum. Somebody's going to critique my Latin. Yes?